Dear all, my name is Aitor Arredondo, doctoral researcher at the UAB, and it's a pleasure to dedicate the following minutes to give this webinar on Magneto-ionics, a practical application to develop coatings for information and communication technologies. As a quick introductory statement, NICKEFFECT aims developing nickel-based ferromagnetic coatings for energy and digital storage applications. In this regard, my work is focused on the development of novel materials candidates for energy-efficient data storage devices. The primary goal of substituting the most used platinum as an essential element present in current magnetic random access memories deals with its scarcity and impossibility to find in mines in Europe. Thus, it results in great strategic interest from the European Union to find an alternative to platinum and, in general, the use of platinum group metals, which are considered critical raw materials. This is especially true in different sectors like electric mobility, digital technologies, and communication technologies. In this sense, the hope relies on finding substitute alternatives based on nickel, which results in being a much more earth-abundant element. Actually, the problem of platinum scarcity is not the only one we are facing. Indeed, considering the progressive increase of global energy demand over the past decades, the current networks and data centers, where magnetic memories form the core of the hardware, require from a vast amount of energy input to function. Looking closely at the power efficiency scale, from the era of the first digital processors back in the 80s to the revolution with the neuromorphic computing devices, a massive energy efficiency increase of up to 11 orders of magnitude has been achieved. This has happened thanks to the design of smaller and smaller transistors, multi-core processors, or non-von Neumann computer architectures. Seeing the tremendous increase in the energy forecast needed for the next few years, it results vital to conceive new methods, strategies, and approaches to create more powerful devices. If we consider that most of the current technologies for data reading, writing, and storage technologies waste a considerable amount of their energy in the form of Joule heating effect, the challenge becomes even more serious. Most of the ICTs used nowadays use either electromagnets or spin polarized currents to switch the magnetic state of the target data writing material, which involves the Joule heating energy and efficiency. At the top left, a simulation image illustrates the Joule heating effect, which relates to a phenomenon where electrical energy is converted into heat after an electric current passes through wire, leading eventually to energy and efficiency in traditional data storage systems. A good example of these are hard disk drives, where the inductive write elements and giant magneto-resistant sensors operate at their high power conditions, which ultimately generates considerable heat and energy loss. And the quest for less energy-consuming devices, where instead of an electric current to solve the magnetism which use an electric field, voltage control of magnetism searches as a promising strategy. Its historical development, beginning with early theories in the 1890s and extending through important advancements in Magneto-ionics from 2014 onwards, have paved the way towards future spintronic devices and magnetic memories. The progression includes interesting concepts like strain, multiferroics, charge density, or electrochemical magnetoelectric control mechanisms. Among different approaches that are included therein, Magneto-ionics involves controlling magnetism via voltage-driven ionic motion. This method shows potential to significantly reduce Joule heating by eliminating the need for current-driven magnetic switching. The timeline below the chart highlights key developments in Magneto-ionics across various ions and mechanisms, such as oxygen, lithium, hydrogen, and nitrogen, among other light elements, and their effects on ferromagnetic, antiferromagnetic, or ferromagnetic states. Concerning the applications of this approach, we can highlight the energy-efficient magnetoelectric devices, neuromorphic computing, spintronic devices, microelectromechanical systems, or sensors, among others. The main advantages of this approach are energy efficiency, thanks to minimizing the dual heating effect, the non-volatility, the multi-material compatibility, and the room temperature operation. Altogether, ensure practicality for real-world deployment without meeting extreme conditions. To introduce the most important outcomes obtained by the UAV related to the goals of the NICKEFFECT project, the first work, titled Composition-Dependent Voltage-Driven Off-On Switching of Ferromagnetism in Cobalt Nickel Oxide Microdiscs, had pretty much unveiled the role of cobalt-to-nickel ratio on magnetoionics of cobalt nickel oxide microdiscs, thanks to non-volatile, reversible off-on-off ferromagnetism switching. To present the material of interest for this work, two oxide compositions, namely nickel 25 cobalt 75 and nickel 50 cobalt 50, respectively, were investigated, achieving full off states through different dynamic conditions as shown by magnetic hysteresis loops in figures A and B. To follow, cross-sectional SEM images, which are shown in figures C and D, reveal a consistent oxide thickness of approximately 1 micron for both compositions. 3D atomic force microscopy images, shown in figures E and F, demonstrate successful wafer scale patterning with clear topographical features. Overall, the purpose is to show that we can control effectively the material properties through annealing and confirm also that structural uniformity and surface patterning are also there in our material, which was the crucial and critical thing for the work's objectives. So this slide presents energy dispersive X-ray characterization of oxides with both compositions. EDX maps show elemental distribution, highlighting that cobalt diffuses faster than nickel, eventually impacting the cobalt oxide nickel oxide bilayer segregation taking place. Two main aspects are discussed. From the diffusivity viewpoint, the diffusion rate of cobalt is higher than nickel, as you can see from the values listed at the reference table. On the other hand, the segregation viewpoint states that due to a lower effective electrochemical contact potential, cobalt preferentially reacts with oxygen atoms as compared to nickel. Actually, these two findings could theoretically confirm why oxygen preferred bonding with cobalt than with nickel, and hence justifying why cobalt went to the topmost part of the discs. The chemical environment of the cobalt nickel oxide microdiscs in the off state was studied through X-ray photoelectron spectroscopy analysis. The cobalt 2p and nickel 2p spectra for two different compositions I studied basically the most cobalt rich and the 50-50 are shown. The fitted spectra indicate the presence of mixed 2 plus and 3 plus oxidation states both for cobalt and for nickel, which indeed validate the previous findings from the X-ray diffraction analysis, where a mixture of cobalt and nickel oxide was found. The experiments suggest that in the off state, both nickel and cobalt exist in mixed valence states, the way we had said before, highlighting the complex oxide chemistry, which is crucial for understanding the material's behavior upon voltage application. The following top left figures display a schematic representation of the electric contacts and the homemade self-setup for in situ liquid-gated vibrating sample magnetometry measurements, where we can see visually all the parts included in the system, and WE and CE represent respectively the working electrode and the counter electrode, which we apply between these two the goal voltage bias. In this case, this bias that I meant was minus 20 volt for the most cobalt-rich composition, and it created the same effect in terms of increase of magnetization as in the most nickel-rich composition with, let's keep an eye on this, 5 times larger voltage. So instead of minus 20, minus 100. So when studying the underlying events, X-ray diffraction and X-ray photoelectron spectroscopy characterization reveal the suppression of some peaks related to the mixed cobalt nickel oxide when switching from the off state to the on ferromagnetic state. In the case of the most cobalt-rich composition, the 101 peak corresponding to the dissolved cobalt-nickel hexagonal cross pact arised. Conversely, for the most nickel-rich oxide microdiscs, negative gating at minus 100 volt for 30 minutes resulted in the suppression of a peak belonging to the orthorhombic nickel 304 phase. Conversely, the 111 and the 200 Miller index peaks corresponding to dissolved phase-centered cobalt nickel appeared. Both phenomena confirm the transition from purely mixed nickel and cobalt oxide to a combination of oxide plus metallic phases in the on state. We can say that this discovery confirms or somehow provides a true explanation of how effective was the electrochemical reduction happened after getting the samples, which was responsible to explain the observed increase in magnetization. To find the theoretical explanation to the dissimilar magnetogenic behavior of the compositionally different cobalt-nickel oxide disks, a combination of molecular dynamics, a universe and machine learning interatomic potential, and DFT calculations was carried out. The vacancy-induced mean square displacements of oxygen atoms, cubic cobalt monoxide, and nickel monoxide were computed as a function of time, using molecular dynamics as reported in the panel of the slide, at a given temperature of 2000 K. So far from this one being a real temperature, this served as a simulated temperature for the computation algorithm to trigger a more dynamic ion movement event during the computation time. Actually, this was the reason for which magnetoionics was faster or more, let's say, energy efficient in cobalt monoxide than nickel monoxide, which justifies why the general magnetogenic behavior of the most cobalt-rich disks is better than in the most nickel-rich ones. So coming now to the second work, entitled Magnetogenic Engineering of Antiferromagnetically RKKY coupled multilayers, the most important milestone was achieving room temperature control of magnetic states in cobalt nickel-based shafts via low voltage magnetogenic effects in ferromagnetically coupled multilayers, thanks to non-volatile, reversible, voltage-induced magnetic multistate level tuning. In this sense, the first study of the aforesaid work was comparing antiferromagnetic, which means compensated, with ferromagnetic, which means uncompensated, synthetic antiferromagnet-based nickel-cobalt multilayer systems. The experimental setup shown in Figure A features multilayers separated by ruthenium interlayer, which is responsible for inducing the RKKY coupling. As a consequence of the indirect spin change in direction between the bottom and top of ferromagnetic layers. To ensure a strong perpendicular magnetic anisotropy, the nickel-cobalt layer thicknesses were optimized, as we can see, to 0.6 nanometer and 0.25 nanometer each layer, respectively. And the magnetic hysteresis loops recorded, shown in figures B and C, show the evolution of magnetic moment versus applied field for different voltage treatments, starting from the Asgron 1 and then following by the application of negative and positive voltage. So the compensated system with 4 cobalt nickel multilayer repetitions in figure B shows a net magnetic moment, while the compensating system in figure C with 5 cobalt nickel repetition shows a respectable near zero net moment. But in the end, the important thing is that we could prove how applying a voltage, in this case of these multilayers, could alter the magnetic properties in both multilayer systems, demonstrating a preliminary Magneto-ionic tunability. Next up, we show a complete vibrating sample magnetometry characterization of ferromagnetically coupled multilayers with 7 bottom ferromagnetic cobalt nickel repetitions and 5 on top, focusing on the effect of the ruthenium spacer thickness for this given ferromagnetically coupled multilayer heterostructure. So things like that. Panel A shows out-of-plane hysteresis loops for different ruthenium thicknesses, revealing distinct switching fields and multi-step magnetization processes, indicating varying interlayer exchange coupling. The strong antiferromagnetic interlayer coupling is observed at the specific ruthenium thicknesses, particularly at the local minima, which corresponds to around 0.6 nanometers. With respect to the panel B, this quantifies this behavior by plotting the exchange field and the resulting exchange energy versus the ruthenium thicknesses, which in both exhibit, as expected, oscillatory behavior, characteristic for sure of these RKKY type interactions. Overall, this data shown in the slide emphasizes the critical role of the ruthenium spacer thickness in tuning the magnetic coupling. To follow, this slide presents a complete VSM characterization of, in this case, antiferromagnetically RKKY, coupled multilayers with 7 bottom ferromagnetic cobalt nickel repetitions and 5 on top, focusing on how magnetic states evolve with voltage application time. Panels A and B show magnetization versus applied field loops for ruthenium thicknesses of 0.9 and 0.4 nanometers, respectively. Increasing voltage duration, so fixing 2 volts and going from 5 to 55 minutes in subsequent time steps, gradually changes the number of magnetic states and the switching behavior, as we can well see in both panels A and B. So panel C quantifies key magnetic parameters over time, such as exchange field in red, the susceptibilities Chi1 and Chi2 in blue, and the normalized remanent magnetizations, which is to say MR1 divided by MS and MR2 divided by MS, marked in green. These results, the outcome that indicates time-dependent modulation of magnetic properties could be achieved in these multilayers, which basically comes along with the multi-state switching of these antiferromagnetically RKKY coupled cobalt nickel multilayers. On the other hand, the similar comparative VSM study, in this case of ferromagnetically RKKY coupled structures, was carried out. In this case, different for sure ruthenium thicknesses were chosen, and the main observation was the increase in the number of magnetic states of the hysteresis loop after the successive voltage application time steps. So for a ruthenium thickness, given a ruthenium thickness of 1.05 nanometer, the number of discrete magnetic states increased from initial 4 to final 6. If we compare the asynchronous states and the 2 volt 55 minutes gated state. This is illustrated in charts A and B, particularly B, and C. There is this 55-minute gating case study. In practical terms, this is of great interest to gain in bit storage areal density, which could trigger tremendously useful for potential high-density memory applications. Next, magneto-optical Kerr effect characterization of a voltage-treated ferromagnetically RQY coupled sample, which is precisely this 1.05 nanometer ruthenium thickness one mentioned and studied at the slide right ahead, no? was attributed some Skillman-like bubble domains with sizes in between 2 and 3 microns in size, which are especially visual at the range of points between 10 and 15, where basically this nucleation of magnetic domains suggests we could even voltage control this nucleation phenomena at the case of this ferromagnetic RQY coupled samples. As a further characterization study, the high resolution transmission electron microscopy analysis proved the oxygen distribution in the gas-grown and voltage-treated states of the static composition multilayer. In this case, the elemental maps and density profiles show how oxygen diffuses into the structure over time, with panels A to C showing the gas-grown state, D to F the gated state of just 10 minutes gating, and G to I the gating state of 2 volt but 55 minutes. So it's clear that the oxygen signal in purple increases and spreads into the top nickel-cobalt layers with increased voltage application time, while the ruthenium in blue remains localized. These observations support the voltage-induced oxygen migration process at the static multilayers. To further understand the atomic scale origin of the magneto-ionic phenomena, X-ray absorption spectroscopy and X-ray magnetic circular decretion characterization was carried out in the studied heterostructure in both gas-grown and voltage-treated conditions. If we closely look at the panels A and B, we can see the X-AS and X-MCD spectra for both cobalt and nickel, highlighting the spectral changes, particularly the emergence of features that indicate the partial oxidation upon voltage treatment, such as we can see this shoulder appearing at the X-AS spectrum. So, conversely, panels C and D quantify the spin-related, orbit-related, and total magnetic moments of the 3 different studied samples, showing a progressive reduction of these magnetic moments with increasing voltage treatment duration, which again is in line with the partial oxidation of both cobalt and nickel, and expected by the previous high-resolution PM analysis. So, as a way to wrap up, let's revisit the main takeaways and the proposed solution to address energy inefficiency in magnetic systems, giving an adequate way to solve the problem towards paving the way to energy efficient magnetic memories. So, with the aim of replacing platinum by nickel in current information and communication technologies, rendering an energy efficient way to control and manipulate magnetism, we've been exploring the concept of voltage control magnetism with a focus on the magneto-ionic approach. This technique allows us to control magnetic properties using voltage instead of current, drastically reducing the energy loss due to Joule heating. In practical terms, we first developed miniaturized cobalt-nickel oxide with finely tuned compositions, which showed promising magnetic performance as demonstrated through techniques like vibrating sample magnetometry. In particular, we can see how applying a voltage can significantly change the magnetization behavior of samples like nickel 25 cobalt 75 oxide, proving that voltage controlled magnetism is feasible in this kind of systems. Secondly, we looked at the RQY coupled cobalt-nickel multilayers. These structures are designed to exploit antiferromagnetic coupling through a ruthenium interlayer thickness. And by applying a voltage, the system we managed to modulate this coupling, enabling precise control over magnetic states at the nanoscale. So together, these advances proven the form of these two works, which are accepted and finished. We could provide a clear path forward for implementing magnetoionics as a solution to energy inefficiency. The range of applications is wide, but we can highlight spintronics, microelectromechanical systems, or even neuromorphic computing as the main features. So those are the final words. Thanks for your attention.